Well, we're now looking at rational functions. And let's see, the word rational is just a fancy word for a fraction, what we might think of as a fraction. 2 over 3, that's a rational number, 2/3 rational number. And in this case, of course, a fraction is just another way of viewing division, if you will. And so when we're talking about rational functions, we're talking about, in our case here, we're going to be talking primarily about what we anticipate in terms of graphing a binomial or polynomial expression divided by another binomial or polynomial expression. Or we could say that it is a function divided by another function. And when we have this, we create in the graph what are called asymptotes. And an asymptote is where a curve is approaching a given line, but that curve of that graph does not cross that line, but it approaches it sometimes just infinitesimally close, but never quite goes over it. And so when we're studying rational functions, we are dealing a lot with asymptotes. And so there's 3 types of asymptotes we can have. Here in this first section, we're going to just consider a couple of them. But there are vertical asymptotes, horizontal asymptotes, and then there are what we call oblique or slant asymptotes, which we'll cover a little bit later in this little chapter. So let's see, a vertical asymptote. And a vertical asymptote, we may also have to consider holes, which we'll look at a little bit later as well. Now, what is going to cause a vertical asymptote? Well, since we're dividing a function by a function, we got variables in both the numerator and the denominator. We know that we cannot divide by 0. And anything that would cause the denominator of our rational function to equal 0 creates an asymptote, because when we try to divide by 0, well, that's undefined. So if we're going to determine the vertical asymptotes, which is what we've got right here, then we are going to factor both the numerator and the denominator. Now, we're going to be thinking primarily about the denominator, but when we talk about wholes, factoring that numerator can become important to us too. So we set the denominator or any of its factors equal to 0, and we solve that, and that is what creates the vertical asymptote. When we talk about wholes, this is a situation which we'll deal with a little bit later in this chapter, but not right now. A whole is where we've got a factor, the same factor, both in the numerator and the denominator, or as it says here, if a factor is upstairs and downstairs. Now, a horizontal asymptote is one in which let me go back up on the vertical asymptote. The vertical asymptote is going to define for us a restriction in the domain. Domain, of course, being x values on the coordinate plane, and this is a value that x could not equal on the graph of this rational function. Now, horizontal asymptote is a restriction in the range, and these can be created as we consider the lead coefficient, or the variable with the highest power. We're looking at both in the numerator and the denominator for the variable raised to the highest power in each of those. And if the numerator is less than the denominator, in other words, the highest power of the numerator is less than the denominator, then the horizontal asymptote is going to be at the point where y equals 0. Now, if the numerator is greater than the denominator, again, I'm talking about the highest power of that variable x. Most of the time we'll be dealing with x. If the highest power of the numerator is greater than the denominator, then there is no horizontal asymptote. But as we may see later, we may in fact have a slant, or what is also called an oblique asymptote, but we'll take that up a little bit later. And if we see a situation where the numerator is equal to the denominator, in order to determine the horizontal asymptotes, we're going to consider the ratio of the lead coefficients of the variables to the highest power in both the numerator and the denominator. And we're going to be taking some look at some examples of that. So I'm going to start off here looking at vertical and horizontal asymptotes of rational functions. Okay, so now I'm over here on page, when it goes from page 131 to page 132. This is example 1, where we're looking to find vertical and horizontal asymptotes. And this particular slide here is corresponds to guided practice 1, which is found on page 132. And what are we being asked to do? We're asked to find the domain of the function and the equations of the vertical or horizontal asymptotes. Now, as you may recall from that previous slide, a vertical asymptote is going to be created wherever in the denominator I have a restriction in the domain, a value that the domain cannot equal, and that would be because it would be triggering an event where x, well, we were trying to divide by 0. For a given value of x, it would cause us to try to divide by 0. So what I want to do in this case, and since I don't have to really factor the numerator and the denominator in this event, I've got x plus 5, and I'm going to now determine the vertical asymptote. So if I take x plus 5 and set it equal to 0 and solve for x, well, x at the point where x is equal to -5, then this would cause me to have to try to divide by 0. -5 plus 5 is going to give me 0. And so x cannot equal that amount in the domain. So the way I would write this as far as the domain is concerned, then I'm going to say that, let me switch color here, that the domain is equal to x such that x cannot equal -5, but x is an element of all real numbers. Now the equation for that vertical asymptote is, and I'm going to abbreviate it, VA, vertical asymptote, just because I don't want to have to write that much, is at x equals -5. Now let's see, what about the horizontal asymptote? Well, the one I want to consider on the horizontal asymptote is the only thing I'm looking at is x raised to the highest power. Now in this rational function, I've got 15x raised to the first power over x raised to the first power. And that's all I really want to consider. This +3, -5 doesn't have anything to do with determining the horizontal asymptote. Now, if you go back to our rules, the highest power of my numerator equals the highest power of my denominator. And so how to determine this horizontal asymptote, I am looking at the ratio of the lead coefficients. Well, even though we don't have a number 1 in front of this x, we know that we assume, since there's nothing there, it's 1. So I've got a ratio of 15/1. And so my horizontal asymptote, which I'm going to abbreviate with HA, is at y equals 15. Okay, let's jump over to the calculator and let's graph this rational function, and let's see if what we have algebraically calculated actually pans out. Okay, so I'm over here at the calculator, and I have gone ahead and entered this rational function. You can see here, and I like to put my numerator and denominator both into parentheses so that the calculator, we'll try to make sure the calculator reads it right. And so here I've got 15x plus 3 over x plus 5, which of course is my rational function. Now, if you recall, let's see, we are anticipating that we're going to see a horizontal asymptote, a vertical asymptote at -5, where x equals -5. And then we would have a horizontal asymptote where y equals 15. And I went ahead and just made a window adjustment. I'll just show you what I did. Because I got a vertical asymptote at y equals 15, I went ahead and just changed my y minimums and my y maximums out to 20 because I want to be able to see as much as I can there. Anyway, so I've got my function equation, my rational function equation entered. I'm going to go to my graph, and I can see here that I do have a curved line. And let's see, x equal -5. 1, 2, 3, 4, 5. -5. So somewhere out here, this graph, and if I could continue to see it going down, it's going to approach -5, but it's never going to go above it. And on the horizontal asymptote, or on the y-axis, let's see, x, y 15, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, somewhere right about here. And of course, these are just values of x up to 10. It's going to be approaching that 15, y equals 15, but it's not going to go above it. Now, one thing before I get out of here, let's go in here to our table. Let's see what I did. Oh, I went way up, so I want to get this back down. What does my table of values look like when x is -5? Let me make this adjustment right here. And we can see here that y is equal to 0. Let's see if I can go back to my table itself. Or it has no value. It's just sitting there at no value. I scrolled way down. Let me just get on down here. Well, before I go, you can see here as x starting to reach some very negative values, we can see that y is getting closer and closer to 15, but it's not ever getting there. Let me scroll on down. This may take a second or two. Sorry about that. Because I want to see when x is -5, what does my table of values show me? Probably going to go in there and set my table set different. Probably should have been quicker that way. All right. When x is -5, I see that I've got an error. It means it cannot equal that. And so there's my vertical asymptote. And let's see if I can go out to, let's say, 100. Start at -15. I'm going to change that. Let's just start at 100, where x is equal to 100. And let me look at my table now. All right, I can see that as x is getting to 100, well, y is 14.3, and as it continues to go up, even out here to 110, well, 14.374 is greater than 14.314, and I can see that it's getting close to 15, but it's not quite getting there. I tell you what, I'm going to go back in here, table set, and I'm going to set this to 1,000. What's happening when x is equal to 1,000? Well, at 1,000, I can see it's at 14,928. It's getting close to 15. And down here at 1,010, it's 14,929. It's getting closer and closer and closer, but it's not going to cross, and it's not going to equal, y is not going to equal 15. Okay, very good. That's it. We'll take a look at one more. Okay, well, let's consider a second rational function. Again, all we're doing right now, we're going to define the domain of the function. In other words, where is our restriction? What can x not equal in the domain of this rational function? And what are the equations of the vertical and horizontal asymptotes? So I'm going to start first with, well, let's see, I could have, let's see, x squared. If I did factor that numerator, I'd have x minus 3 times x plus 2, which is not equal to x plus 4. So I'm not going to have a hole in this. We'll be talking about holes later. So I'm really just going to focus here on x plus 4 to do two things. Find what my restriction in the domain is and what where my vertical asymptote is going to lie. And I'm going to set this denominator equal to 0. So I'm going to say x plus 4 equals 0 and x equals negative 4. So at the point in the coordinate plane where x is equal to negative 4, I'm going to have a vertical asymptote, and this also defines the restriction in my domain. So I'm going to write my domain like this. I'm going to have d equals, put a bracket here, x such that x does not equal negative 4, but x is an element. Otherwise, x is an element of all real numbers. Make a little fancy R, 2-bar or R. And I'm going to say that my vertical asymptote is, the equation for that is x equals negative 4. Now, what about my horizontal asymptote? Now, again, on my horizontal asymptote, the only thing I'm going to consider is the power of x raised to the highest power in both the numerator and the denominator. So here I got x squared, and here I've got 1x. So the power of my numerator is greater than the highest power of my denominator. And that's going to tell me, because of that, because of the rule we looked at the opening slide, that I am not going to have a horizontal asymptote. There is none. Or I could just say there's no horizontal asymptote. Now, we may discover a little bit later on there's an oblique or slant asymptote, but again, we'll take that up later. Now, we're going to jump over to the graph, see what the graph of this rational function looks like. Okay, so here I'm back at y equals, and I have, again, for save a little bit of time, gone ahead and entered the rational function where I've got, and I put both in, I put in the parentheses, x squared minus x minus 6, close my parentheses, divided by, in parentheses, x plus 4. So there's my rational function. I'm looking to see that I'm anticipating that I'm going to see a vertical asymptote at negative, where x is equal to negative 4, because I cannot divide by 0. It's going to restrict my domain to where x cannot equal negative 4, but other than that, it can equal all other real numbers. And I don't think I'm going to have a horizontal asymptote. So let's see what the graph looks like here of this rational function. And so we see it coming here from way up above. And right out here, let's see, negative 4 is right out here. So it's obviously not going to cross this negative 4, and it comes down, and then boom, it just takes off out here out to infinity. And I'm going to take a quick peek at my table. I went back and reset my table, reset my window settings. And I'm going to go in here to the table, second graph, give me a table. And I can see right here at negative 4, I've got an error. That means that x cannot equal negative 4 in this particular function. And then this gives me all my other y values. I see it when x is negative 3, y is 6. When x is 0, y is negative 1.5. And when x is 5, it moved back out to positive territory, where it's valued at roughly a half. I'm going to just go back to my graph again. And there I see what my table of values also show me as it moves out here towards infinity. Okay, well, not bad. We'll be looking at some more.